Hello, this is Andrew Xiangfen. Welcome to my presentation on Dijkstra's algorithm. This algorithm, developed by Dijkstra in 1956, is one of the most efficient ways to calculate the shortest paths in weighted graphs. Today I'll demonstrate how this algorithm works using this graph inspired by a certain man, and it's going to represent something greater. It's going to symbolize something more precious than anything else. And it's like we're going to use this adjacency matrix. So let's first focus on this adjacency matrix. So what do you see? You see the main gate. Okay, so it's gonna be a building of some sort. You got the garage. Gotta house those cars, Got the living room, so it's gonna be a house. The garage, the main gate, the living room, it's gonna be a house. Then you got the gym. Gotta get your body right. Got the kitchen. Same thing. Gotta get your body right. Gotta get those nutrients in. Got the basketball court. It's a basketball player. You got the rooftop lounge. So what does that mean? You got the huzz. That's what it means. You got the swimming pool. Cardio. Everybody needs some cardio. So what is this? You got 8 locations. 1, 2, 3, 4, 5, 6, 7, 8. And this is LeBron James. LeBron James's mansion. It's not a house. It's a mansion. Remember that. Mansion. And who is LeBron James? He is the GOAT. Okay. So we're gonna use this LeBron James's mansion to show how this algorithm works. And each vertex. So let's consider this adjacency matrix again. Each vertex represents a location, such as the main gates, garage, and gym, and the edges. So these things represents the time, the walking times. It's because on Google Maps, you don't want to be looking at how many miles it is. You want to see how long it takes you to get there. That's what everybody wants, and that's what LeBron wants. So we have made this adjacency matrix for LeBron. Okay, so let's first get into Dijkstra. Edgar Dijkstra was a computer scientist from the Netherlands. Pretty cool place. And he developed this algorithm to solve a routing problem. Fun fact, this was for the Dutch Postal Service. And so he's Dutch. Dijkstra is a Dutch name. It's a stupid name. And that's how you know it's Dutch. Today, it's widely used in applications such as GPS navigation. Obviously, it's a mapping algorithm working with maps. And then you got the network routing, and then you got logistics. And so before we dive in this algorithm, let's start with the graph creation process. Okay, so to build our graph, we start with this adjacency matrix. This matrix is a 2-dimensional table with rows and columns representing vertices in the graph, and each cell contains the weight of the edge connecting two vertices. In our example, the adjacency matrix represents walking times between locations in LeBron's mansion. For example, the value. Okay, so the value of gym. So let's take the row gym and the column swimming pool. The row gym and the column swimming pool. So what does this get us? This gets us a value of 9. So it takes him 9 minutes. So once he gets his workout in with weight training, goes to the swimming pool for some cardio. Okay, so we're going to, we have these values, so it's going to take 9 minutes. And so based on that, we can start interpreting this visualization. This is a visualization of the Dijkstra images. It's a graph. Okay, so let's use, once you get the adjacency matrix with the graph, now let's start from the beginning. So you're gonna obviously walk in through the main gate. Let's locate the main gate. The main gate's right here. Okay, so the main gate, we start off with a chart. So we set the main gate as 0, and then we set everything else initialized to infinity. This makes sure that the starting vertex, the main gate, is the starting main vertex, because we have that gate as 0. But then we haven't gone anywhere yet. We're still at the main gate. So we're gonna set everything else to infinity to ensure that we get to the places that we want to go. So the living room. So we're gonna just put on everything. So the living room, we have the garage, we have, the basketball, the basketball court. We've got the kitchen. We got the gym, the swimming pool. And the rooftop lounge. So 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8. So once we set the main gate to 0, because that's our starting, we can set everything else to infinity. And it doesn't need to be infinity. It just needs to be a big number, bigger than anything else, so that we can ensure that there's not going to be any crossovers, and then everything's going to work fine. So once we get from the main gate, we're going to look at its neighbors. So from the vertex, the main gate, there's 2 neighbors. It's the living room and the garage. So because we know these values of like how long it's going to take them to get from the main gate to the garage, because it says it right there, we got 3 and 5 respectively. So from the main gate to the garage, it's going to be 3. So we can update that. Instead of infinity, we can say it's 3. And from the main gate to the living room, it's going to be 5. So we can update that too. And so what can we do right now is also include that the main gate to the living room is the path to go. And so then the main gate to the garage is also the path to go. So once we reached all the neighbors, the unvisited neighbors of the main gate, we can label the main gate as visited. So we'll use highlighting, say that the main gate has been visited. The main gate has been visited. And so then what do? We look at the unvisited places, the unvisited vertices, and see which one is the least. And so right now, 3 is the least. So the garage. So we'll go on to the garage. The garage touches the living room and the gym. So with the living room, what does that mean? So it's going to be from the main gate, so 3, from the garage to the living room, it's 2. So it's going to be the same distance. 3 plus 2 is 5. So there's no point in updating it. You can obviously add in if you want that you can go from the the main gate to the garage to the living room. We can do that. But it's still going to be the same distance of 3 plus 2, 5 minutes walking either way you want to go. And then the garage to the gym is an extra 6 minutes. So 3 plus 6 would be 9. So using the edges, we can say that from the main gates to the gym, it's going to take them 9 minutes. So 9 minutes. So the gym, we can update that to 9. This is infinity. Okay, so with the gym, we can say that it's from the main gate to the garage to the gym. Okay. Once we got that set, we can say that this has been visited because it has been visited. So then we go on to the next one. So what is the next least one? Let's say that the garage is. Okay, what's the next least one? 5, infinity, or 9s. The infinities are the 9. And so it's going to be the living room. So from the living room, what are its unvisited neighbors? It's going to be the basketball court or the kitchen. So the basketball court, let's focus on that first. It's going to be an extra 7. So 5 plus 7 is 12. So basketball court, we can update that as 12 from the main gates to the living room to the basketball court. That's going to be 12. And then from the living room to the kitchen, it's going to be an extra 2. That's going to be 7. So kitchen can be updated to now to 7. So main gate to living room to kitchen. Okay. And so now that we got this information, because it's going to be 7 and 12, now the living room has been visited too. So let's label that as such. So we got three vertices covered. So now let's look at the rest of the unvisited ones. So it's 12, 7, 9, or infinity. 7. Okay, so from the kitchen, there's going to be 2. So the swimming pool or the rooftop and the rooftop lounge. So from the main gates to the swimming pool, it'd go from the main gates to the living room to the kitchen to the swimming pool. So that'd be an extra 4. Is that 4? Yeah, that's 4. 4 added on to the kitchen. So the kitchen right now is 7. That'd be 11. So it's going to be main gate to living room to kitchen to swimming pool. Okay, so that means that we can just highlight this as kitchen. We stopped at rooftop lounge. So from the kitchen, it's going to be an extra 5. So extra 5. That's the kitchen. Is going to be 12. To the living room. Main gate to the living room. To the kitchen. To the rooftop lounge. Okay. So once we got that, we have visited the 2 neighbors. Unvisited neighbors of the kitchen. The kitchen is out. Kitchen is visited. Okay. So now let's go on to the next one. So it's going to be 9. The gym. The gym. 2. The same 2. It's going to be the swimming pool and the rooftop lounge. Swimming pool would be an extra, is that 9? Yes, I believe so. So it's going to be 9. Gym gym to swimming pool, extra 9. Gym right now is 9. 9 plus 9 equals 18. The swimming pool, 18. So it's 11 greater than or equal to 18. It's less than. And so right now we want the shortest path. So we're going to keep with the pre-existing swimming pool path. So we're just going to leave that there. There's no need to update. And then the rooftop lounge. Okay. So right now it's going to be 9 plus 8. Same thing. It's 12 less than or equal to or greater, less than or greater than 17. It's going to be less than. So we're going to keep that too. Okay. So those two are still the same. And since we've visited both of his neighbors and nothing turned out, we can now say that the gym has been visited. Obviously, if you found a shorter path and it worked out, you can update it. And you have done like all the you've compared everything and you've seen if it's shorter or not, or if it's longer, then you'd obviously update it. But in my case right now, because LeBron James had it set up so perfectly, his house so perfectly, we're not gonna update it. And that's a nod to LeBron James, So I don't have to do any work right now. So then we go on to the next one. So it's gonna be 11 or 12. It's gonna be 11. But the swimming pool has no more neighbors. So, no more neighbors that have been visited, haven't been visited. So we can say that the swimming pool as well has been visited. And then same thing for the rooftop lounge and the basketball court. Rooftop lounge and the basketball court. So everything has been visited. Everything has its path I can go. So to go down the line, main gate is the starting point, 0. Living room, 5. Either from the main gate to the living room directly, or the main gate to the garage to the living room. The garage from the main gate to the garage is going to be 3, shortest distance. Then you have the basketball court, 12 minutes, main gate to the living room to the basketball court. You got 7 for the kitchen. It's going to be the main gate to the living room to the kitchen. You got the gym, which is going to be the main gate to the garage to the gym, 9 minutes. 11 minutes for the swimming pool, main gate to the living room to the kitchen to the swimming pool. 12 minutes for the rooftop lounge. It's going to be one of the later ones because LeBron James needs to have that alone time with that woman, the woman, the huzz. And so, make it to the living room, make a detour to the kitchen, and ultimately end up on the rooftop lounge. Okay, so that's how Dijkstra works. Dijkstra is quite brute force, as shown here, but what we call Dijkstra is a greedy kind of algorithm. It focuses on local areas, so it focuses on specific places, and it sees its neighbors. It sees its neighbors to see the shortest path. It's all local. It's all focused on one part, and so that's what it means by greedy. Dijkstra is also one of the building blocks. You see, Dijkstra was developed in the 50s, 1956, but in these decades, since we've developed it more, we have worked on it, and so Dijkstra right now isn't it's the cornerstone, but it's not the premier. It's not the most the strongest, the quickest, the most efficient way to find the shortest path to your destination. They're gonna be like the type of AI kind of work where it's like the machine learning. It'll send multiple like configure it's gonna process multiple ways, so it might go this way and this way at the same time to try to find the shortest path. Because if you do it 2 times, obviously you're gonna find the answer quicker. There are also algorithms like A search, because they are generally considered more efficient than Dijkstra's algorithm, especially when you have a good heuristic function that can like guide the search towards the goal more directly. You have the Bellman-Ford algorithm, because unlike Dijkstra's algorithm, Bellman-Ford is capable of handling graphs in which some of the edge weights are negative. So what's the point is that Dijkstra is like the poppy. It's like the old goats. It's like Michael Jordan. LeBron James has built his mansion. He's built his career off of other people. So that means that he's the GOAT now. Like Dijkstra used to be the GOAT, like Michael Jordan. LeBron James is now the GOAT of everything. He's the GOAT of basketball. And so now Dijkstra just works in his favor because it just makes him better. And so what I'm getting to at is you got Dijkstra now. You got how it's a brute force. You got how like the process works, the updating. And everything works out fine when you use it correctly. And it's the most basic way. It's the most reliable way for a reason. Dijkstra works. I love you.